Hello everyone. In today's video, I will discuss about ligand retrieval and preparation. In this video, first we will learn all about ligand retrieval and preparation theoretically. Then we will do all these how ligand retrieval and how to do preparation practically. Before we perform molecular docking, we need two essential components, a target protein and a ligand. The protein acts as the biological target while the ligand is the small molecule that binds to this target. However, simply downloading a ligand from an online database is not enough. The downloaded structure usually requires preparation before it can be used for docking. This preparation improves the quality and accuracy of docking result. In this video, I will explain what a ligand is, how to retrieve ligands from public databases, how to prepare ligands for docking, why energy minimization is important, how to convert ligand file format, Lipinski rule of 5, and finally drug likeness and ADME evolution. By the end of this video, you will understand the complete workflow of ligand preparation before molecular docking. First, I will introduce ligand retrieval and explain why it is important. Next, I will discuss the three most widely used chemical databases like PubChem, ChEMBL, and Zinc database. After downloading ligands, I will explain ligand preparation, which includes energy minimization, geometry optimization, and file format conversion. Then I will discuss Lipinski rule of 5, which helps determine whether a compound is likely to become an oral drug. Finally, I will explain drug likeness and ADME properties, which help predict whether a compound has a suitable pharmacokinetic characteristics before experimental study. What is a ligand? Before learning ligand preparation, we should first understand what a ligand is. A ligand is a small molecule that binds specifically to a protein target. This binding may activate or inhibit the biological activity of that protein. In molecular docking, the ligand is treated as the query molecule while the protein acts as the receptor. Docking software predicts how strongly the ligand binds to the protein and identifies the best binding orientation. So ligand can be classified into three major categories. The first category is natural compound. These are molecules obtained from plants, microorganisms, or marine organisms. Many traditional medicines and herbal compounds belong to this category. The second category is FDA-approved drugs. These compounds already have established safety profiles and are commonly used for docking drug repurposing studies. The third category is synthetic molecules. These are chemically designed compounds optimized to interact with specific protein target. An important point to remember is that ligand quality directly affects docking accuracy. Poor quality ligand structure may lead to incorrect docking poses and unreliable binding energy prediction. Therefore, proper ligand preparation is essential before molecular docking. Once we know the target protein, the next step is ligand retrieval. In previous video, we will learn about how to prepare protein for docking. In this video, I will show you practically how to retrieval ligand and how to prepare ligand. Okay, so ligand retrieval measure database is here. Once we know the target protein, the next step is what? Ligand retrieval. Ligand retrieval means downloading chemical structures from publicly available databases. The first database is PubChem. So PubChem is one of the world's largest free chemical databases maintained by the NIH. It contains millions of chemical compounds. Structure can be downloaded in SDF, MOL, SMILES, and other formats. The second database is ChEMBL. Unlike PubChem, ChEMBL focuses on bioactive molecules. It contains experimental biological activity data. Therefore, ChEMBL is especially useful when selecting compound with experimentally validated activity. The third database is Zinc. So Zinc provides commercially available compounds that are already prepared for virtual screening. It includes natural products, FDA-approved drugs, and perishable compounds. Many docking studies use zinc because the compounds are already formatted for computational workflow. So each database serves a different purpose. PubChem for journal compound searching, ChEMBL for bioactivity information, Zinc for virtual screening and ready to dock compound. And in this slide summarizes the complete ligand preparation workflow. The first step is selecting the target. For example, in my study, I selected the protein with PDB ID 6I81. The second step is searching for ligand in databases such as PubChem or ChEMBL. The third step is downloading the ligand, usually in SDF format. Next comes ligand preparation. During this stage, we optimize the molecular geometry and add hydrogen atoms, assign charges, remove structural errors, and prepare the ligand for docking. Finally, the prepared ligand is converted into PDBQT format, which is required by AutoDock. Following this workflow ensures that every ligand entering molecular docking is chemically correct and computationally ready. So ligand preparation, why it's matter? Now let's understand why ligand preparation is necessary. The ligand downloaded from database is usually not ready for docking. Many downloaded structures contain missing hydrogen atoms, incorrect bonds, angle unrealistic geometry, undefined atomic charges, or steric classes. If we directly use these structures, docking results become inaccurate. So ligand preparation solves this problem. During preparation, molecular geometry is optimized, hydrogen atoms are added, partially charges are assigned, and the lowest energy conformation is generated. This process produces a more realistic ligand structure that better represents how the molecule behaves inside a biological system. Prepared ligands generally produce more reliable docking scores and better binding predictions. I already explained you ligand preparation why it's matter. Now we will move further. Energy minimization and file format conversion. Energy minimization is one of the most important steps in ligand preparation. Every molecule naturally prefers the lowest possible energy state. Sometimes downloaded structures contain steric classes, unrealistic bond angles, or strained conformations. Energy minimization adjusts atomic positions until the molecule reaches a stable and low energy conformation. This increases docking accuracy because the ligand resembles its biologically stable structure. After energy minimization, the ligand file must be converted into compatible formats. Usually the workflow is SDF to PDB to PDBQT. The SDF file is downloaded from PubChem or Zinc. The PDB file can be generated using Discovery Studio, or you can use also OpenBabel. Finally, AutoDock tool converts the PDB file into PDBQT format by assigning charges and defining rotatable bonds. PDBQT is the final format required by AutoDock for docking. In this slide, before docking, we evaluate whether the ligand has drug-like properties using Lipinski rule of 5. Okay, so in this slide, we will learn all about Lipinski rule of 5. This rule was proposed by Christopher Lipinski. According to this rule, the molecular weight should be less than or equal to 500 daltons. The log P value should be lesser than or equal to 5. Hydrogen bond donor should not exceed 5. Hydrogen bond acceptor should not exceed 10. Additionally, parameters include rotatable bonds should generally be less than or equal to 10, and the topological polar surface area should be below 140 square angstroms. Compounds satisfying these criteria are more likely to have good oral bioavailability. However, remember that Lipinski rules is only a guideline. Some successful drugs violate one or more of these rules. Drug likeness or ADME evolution. After Lipinski analysis, we evaluate ADME properties. ADME stands for absorption, distribution, metabolism, and excretion. Absorption predicts how efficiently the drug enters the bloodstream after administration. Distribution describes how the drug travels throughout the body, including plasma, protein binding, and blood-brain barrier penetration. Metabolism predicts how liver enzymes, particularly CYP450 enzymes, process the drug and whether harmful metabolites may form. Excretion explains how drug is eliminated through urine, bile, and feces. Several free online tools can predict these properties, including SwissADME, PKCSM. These computational predictions help researchers prioritize promising compounds before performing laboratory experiments. In conclusion, ligand retrieval and preparation are essential steps in molecular docking. Proper preparation improves docking accuracy, enhances prediction reliability, and increases the chances of identifying potential drug candidate. So now we will move on practical and how to retrieval any ligand from the different databases and how to prepare ligand for docking. Now I will demonstrate how to retrieve a ligand from the PubChem database. For this tutorial, I will download the ligand JQ1, which I will later prepare for molecular docking with my target protein 6I81. Before starting the docking process, We need a reliable three-dimensional structure of our ligand. PubChem is one of the most widely used public chemical database maintained by the National Center for Biotechnology Information. It provides detailed information about millions of chemical compounds, including their structures, properties, biological activities, and downloadable file format. So first I open my web browser and search PubChem. This is the official website of PubChem. On the home page, you can see a search bar where we can search by compound name, molecular formula, CID or SMILES, nations. Search for the ligand here. Here we can see important detail all about our ligand. So PubChem displays the compound information page. So here we type JQ1. This is our targeted ligand, those we use for molecular docking. Here we can see important details such as the compound name, molecular formula. You can see here molecular formula, synonyms, and pharmacologic biological activities, safety information, and experimental properties. All information regarding the ligand available here. You can see molecular formula and compound CID, IUPAC name, SMILES. So basically when we analyze ADME, we use SMILES. Scroll down, we can also find additional information. You can see here these all are the ligand but different molecular formula. Next, I locate the 3D conformer of the molecule. The three-dimensional structure is important because molecular docking requires the spatial arrangement of atoms to predict how the ligand bind to the protein. You can see here 2D structure available and 3D structure available. Both structure are available here. You can see here, if you click here, now you can see the structure here. This is the structure of JQ1. This is the 3D structure. Click on stick. Now our ligand convert into stick form. If we click on wireframe, you can look. You can see here our ligand like this. Basically, if we click, then you can see you can zoom by clicking on plus. You can minimize the. Now I click on the download option. Here. Several file formats are available including SDF, MOL, SMILES, JSON and XML. You can see here. For molecular docking, we need 3D structure of ligand because it contains atomic coordinates required for ligand preparation. So but here I download 2D structure because I will show you how to convert 2D structure into 3D structure by using Discovery Studio. Now our structure is downloaded. I click download and the SDF file is saved to my computer. Okay, so why SDF? The structure data file or SDF stores detailed information about the molecule including atom coordinates, bond connectivity and molecular properties. Most molecular visualization and docking software can read this format. At this stage, our ligand has been successfully retrieved. However, this downloaded file is not yet ready for docking. In the next step, we will prepare the ligand by checking the molecular structure, performing energy minimization if required, adding hydrogen atoms, assigning atomic charges, and finally converting the ligand into PDBQT format, which is required by AutoDock. These preparation steps improve docking accuracy and ensure reliable binding predictions. That's all for ligand retrieval from PubChem. Now I will demonstrate how to perform ADME analysis of a ligand using the free online tool SwissADME. Before investing time in molecular docking or laboratory experiments, it's important to evaluate whether a compound has suitable pharmacokinetic properties. ADME analysis helps us predict how a drug behaves inside the human body. ADME stands for A. Absorption, D. Distribution, M. Metabolism, E. Excretion. SwissADME predicts these properties based on the chemical structure of the ligand. First, I open my web browser and search for SwissADME. Now I open the official SwissADME website. The homepage contains a text box where we can paste the chemical structure of our compound in SMILE format. You can see here, enter a list of SMILE here. Now I go to PubChem and search my ligand. Like I targeted GQ1 ligand for docking with protein. On the compound page, I scroll to conical smiles. I copy the complete smile lesion because SwissADME accepts smile as the input for prediction. Then I return to the SwissADME website and paste the smiles into the input box. On run button. Now understand the results. Let's interpret the result one section at a time. Physiochemical properties. The first section contains the basic molecular properties. Here we can see molecular formula, molecular weight, number of heavy atoms, aromatic atoms, rotatable bonds, hydrogen bonds, hydrogen bond donors, hydrogen bond acceptor, topological polar surface area, also known as TPSA. You can see here number of rotatable bond 5, number of hydrogen acceptors 5, and molecular weight is less than 500. These ligands follow the Lipinski rule of 5. These properties help us understand the chemical characteristics of the molecule. When I taught theoretically I was already explained all about Lipinski's rule of 5. Okay, so Lipinski rule predict whether a compound is likely to be orally active. The important criteria are molecular weight should generally be less than or equal to 500 Dalton. Log P should generally be less than or equal to 5. Hydrogen bond donor should be 5 or fewer. Hydrogen bond acceptor should be 10 or fewer. If a compound violates multiple rules, it may have poor oral bioavailability. For larger natural products or anti-cancer drugs such as vincristine, some violations are expected because these compounds are often administered intravenously rather than orally. Water solubility. The next predicts water solubility. Water solubility affects how easily a drug dissolves in a body fluid. Generally, compounds with better solubility are absorbed more efficiently. SwissADME classified compounds as soluble, moderately soluble, poorly soluble, insoluble. You can see here the water solubility of our ligand. Next is pharmacokinetics. Now let's examine the pharmacokinetics properties. SwissADME predicts GI absorption. This indicates how efficiently the drug is absorbed through the gastrointestinal tract. High GI absorption suggests better oral absorption. Low GI absorption indicates limited oral bioavailability. Blood-brain barrier permeability. So, blood-brain barrier permeability. This predicts whether the compound can cross the blood-brain barrier. For drugs targeting the brain, BBB permeability is desirable. For drug targeting other organs, lack of BBB penetration may reduce unwanted neurological side effects. Next is P-glycoprotein substrate. SwissADME also predict whether the compound is a substrate of P-glycoprotein. P-glycoprotein is a transporter protein that pumps drugs out of cells. If a compound is a substrate, its intracellular concentration may decrease, which can reduce therapeutic effectiveness. Next is cytochrome P450 inhibition. SwissADME predict interaction with major CYP450 enzyme, including A2, 19, C9, D6, A4. These enzymes metabolize many drugs in the liver. The compounds that inhibit CYP enzyme may increase the risk of drug-drug interaction. Next is drug likeness. SwissADME also evaluates drug likeness using several rules such as Lipinski, Gaussick, Weber, Egan. Passing these filters suggests that the molecule has physiochemical properties commonly found in successful drugs. Next is medical chemistry. You can see here medical chemistry. Finally, SwissADME predict medical chemistry properties. These include Payne's alter, which identifies structure that may produce false positive biological results. Brent alters, which detect potential problematic chemical fragments. Synthetic accessibility score, which estimate how easy or difficult it is to synthesize the compound. So lower synthetic accessibility values generally indicate the molecule is easier to synthesize. So conclusion is to conduct SwissADME is a powerful and free web-based tool that allows us to evaluate a compound's pharmacokinetic properties before molecular docking by analyzing absorption, distribution, metabolism, excretion, and drug likeness. We can identify promising drug candidates and eliminate compounds with poor pharmacological properties at an early stage. In my work, I perform ADME analysis before molecular docking to ensure that the selected ligand has suitable drug-like characteristics. So now we will move further. Now I will demonstrate how to convert 2D SDF file into a 3D structure using Discovery Studio Visualizer. First, open your downloaded ligand. So click on File and go on Open and select your downloaded structure. You can see here the 2D structure available here, and now our structure in 3D form. You can see here. Now save this structure. Click on File. Save your structure in PDB form and rename the name of ligand. I provide a suitable file name such as JQ1, JQ1, and click Save. Now ligand has been successfully converted from a 2D SDA file into a 3D PDB structure. Why is this step important? Let's briefly understand why this conversion is necessary. Our 2D structure only describes the connectivity of atoms. However, molecular docking predicts how a ligand fits inside the binding pocket of a protein. This process requires the exact three-dimensional coordinates of every atom. Generating a 3D structure provides a realistic molecular conformation, which improves the accuracy of docking studies. At this stage, our ligand is now available in 3D PDB format. However, it is still not completely ready for docking. Now you can reopen again your converted structure. Those are in PDB form. So click on File, then Open. Open your converted JQ1.pdb structure. Now you can see here 3D structure available. You can rotate and see. You can see here chains, atoms, ligand groups. Now I will demonstrate how to prepare the JQ1 ligand for molecular docking using AutoDock tool. So basically ligand preparation is a crucial step because AutoDock requires a properly prepared ligand with hydrogens, atomic charges and rotatable bonds to predict accurate protein ligand interaction. So first open your AutoDock tool, then click on File, read molecule and select the ligand file jq1.pdb that we generated using Discovery Studio. The PDB file contains the three-dimensional coordinates of the ligand, which will now be prepared for docking. Now it's time to add hydrogen. So click on Edit, select hydrogen, add polar hydrogen here. Polar hydrogen are added because they participate in hydrogen bond formation with amino acid residues inside the protein binding pocket. These interactions are important for accurate docking prediction. Now our hydrogen is added here. You can see here these bright color show hydrogens. Now compute Geiger charges. So go on edit, click on charges and add compute Geiger. Now charges added here. Geiger charges assign partially electrical charges to each atom in the ligand. These charges are essential because AutoDock uses them to calculate electrostatic interaction between the ligand and the protein. Now detect the root atoms. So click on ligand, then click torsion tree and detect. Now again go on torsion tree ligand, then click on torsion tree and detect root. You can see here now root is detected. The root atoms act as the reference point of the ligand during docking. AutoDock automatically selects the most suitable atom to serve as the center for ligand rotation. Now it's a center of root, you can see here. Now define rootable bond. So select again ligand, click on ligand, go on torsion tree, choose torsion. Autodock automatically identify all single bonds that can rotate. These rotatable bonds allow the ligand to change its conformation while searching for the best binding pose inside the protein. Carefully inspect the ligand to ensure that hydrogen's atomic charges and rootable bond has been assigned correctly. This quality check helps prevent errors during molecular docking and improves the reality of the docking results. Again, I say this quality check helps prevent error during molecular docking and improves the reliability of the docking results. Okay, so now our structure is ready for dock. So we move further to save the ligand as PDBQT. So click on ligand and then click on output and save as a PDBQT. The PDBQT format stores the ligand's atomic coordinates, atom types, Geiger charges, and torsion information. This is the format required by AutoDock for molecular docking. Now click on Save. Our ligand structure is ready for docking. So conclusion is the ligand preparation process is now complete. We have successfully added polar hydrogen, assigned charges, detected the root atoms, defined rootable bond, and saved the ligand as PDBQT format. Now let's quickly summarize today what we learned. Okay, so we learned the complete workflow of ligand retrieval and preparation before molecular docking. First, we understood all about ligand retrieval and ligand preparation theoretically. We understood what a ligand is and why selecting a high quality ligand is important for obtaining reliable docking results. Next, we explored The major chemical databases PubChem, ChEMBL, and Zinc, and learned how to retrieve ligand in the associate file format. After retrieving the ligand, we discussed ligand preparation, including converting the structure into a 3D model, performing how to add hydrogen atoms, assigning charges, detecting rotatable bond, and converting the ligand into the PDBQT format required by AutoDock. We also learned about Lipinski rule of 5, which help evaluate whether a compound has drug-like properties suitable for oral administration. Finally, we explored ADME analysis, which predicted the absorption and distribution, metabolism, excretion properties of a compound. These predictions help identify promising drug candidates before molecular docking and experimental studies. Overall, proper ligand retrieval and preparation are essential because they improve the accuracy, reliability, and reproducibility of molecular docking studies. With this, I come to the end of my presentation. Thank you all for your time and attention. I hope this all tutorial helped you understand the complete ligand retrieval and preparation workflow used in computer-aided drug discovery. If you have any question or suggestion, I would be happy to answer them. If you have any type of doubt, drop your doubt in comment box and contact us on this mail ID and this contact number. Thank you. Thank you and have a wonderful day.